In our previous video, we talked about relational operators and logical operators. And in this video, we are going to talk about bitwise and assignment operators. So without further delay, let's get started. Now before we talk about bitwise operators, we must first understand what are binary numbers and how to convert a decimal number into binary. I have already uploaded a video on binary numbers. You can go and check it. The link will be in the description. And after you have watched it, you can come back and continue from here. So it's important to know about binary numbers before we jump into bitwise operators, because bitwise operators ultimately use binary numbers. So what are bitwise operators? These are the operators that work directly on the bits of a binary number instead of a decimal number. So far the operators that we use work with decimal numbers, but this bitwise operator works with binary numbers, the bits of binary numbers. There are in total 6 bitwise operators, and the first one that we are going to talk about is AND operator. Let's first quickly declare and initialize two variables. Let's say I name it operand 1, and let's say I initialize it to 3. And let's declare and initialize another variable. Let's name it operand 2, and let's say it is initialized to 2. Besides these two variables, we need to declare another variable that will store the result, and we are going to initialize it to the result of bitwise AND operator. An AND operator is specified in C with a single AND. So if I write double AND, this is a logical AND operator, and if I write a single AND, then this is a bitwise AND operator. And as we know, these decimal numbers are internally represented as binary numbers. So this 3 is represented as 1 1, and this 2 is represented as 1 0. And this AND operator is going to work on these binary numbers instead of the decimal numbers. Okay, so this bitwise AND operator is going to work like this. It takes the first bit from the first operand and the first bit from the second operand and compares them to see if both of them are 1. If both of them are 1, it's going to return a 1. Otherwise, it's going to return a 0. In our case, we see that one of the bit is 0. So this is going to return a 0 for the first bit. Then it's going to check the next bit from the first operand and the next bit from the second operand. So it's going to compare them to see if both of them are 1. And as you can see, both of them are 1. So this is going to produce a result of 1. And remember that 1 is also known as true, and the 0 is also known as false in C. So this is going to be the result of this bitwise AND operator, and this binary number represents number 2. So this bitwise AND operator is going to return a value of 2. So if I print the value of result variable, you see a value of 2 as expected. Let's try one more example. Let's say I change this to 4, and the binary representation of 4 is 100, and for 2 is 10. This 0 does not matter. So if I do AND operation starting from the first bit from each operand, AND is going to return 1 if both the bits are 1. As you can see, both the bits are 0, so this is going to return 0. Similarly, in the second bit also we don't have both the bits as 1, so this is also going to return 0. And the last bit, both of them are not 1, so this is also going to return 0. Now this is a representation of 0, so in this case we are going to return a value of 0. So if I run this, we see a value of 0 as expected. Okay, now let's talk about another bitwise operator known as OR operator, and it is presented with this straight line. In case of AND operator, we saw that if both the bits are true, we return a value of true, otherwise false. But in case of OR operator, we not only check if both the bits are true, we also check if one of the two bits are true. So it's going to return true if one of the two bits are true or both the bits are true. So it's going to return false when it encounters both the bits as 0. So in our case, both the bits are 0. So this is going to return as 0. And in our next bits, we see that both of them are not true, but one of them is true. So this is going to return 1. And in our last bit, we see that one of them is true. So this is also going to return a 1. And this is a representation of decimal number 6. So if we run this program, we should get a result of 6. So if I run this, you see a value 6 printed on the screen. Let's take one more example. Let's say I change this to 3. And this can be represented in binary as. So we first check if both the bits are true. Both the bits are not true. So then we check if one of the two bits are true. And as we can see, this bit is true. So this is going to return a value of true, which is 1. Similarly, in our next bit, we also see the same sequence of bits. So it's also going to return 1. And in the last, we see that one of the bit is true. So this is also going to return 1. So this is the binary representation of decimal number 7. So if I run this, this should produce a result of 7. So if I run this, you see the value 7 printed on the screen. Okay, coming to our next bitwise operator, which is exclusive OR, also known as XOR, which is represented with this caret sign. And this exclusive OR operator works like this. If it encounters one of the bit as true and other as false, then it's going to return a value of true. Otherwise, it's going to return a false. So if both the bits are true or both the bits are false, then it's going to return a value of false. In our case, we see one of the bit is set to false and other bit is set to true. So in this case, it's going to return a value of true. Similarly, in our next bit, we see the same pattern. So it's also going to return a true here, which is 1. And in the last bit, we see one of the bit is set to 1, other is false. So here it's also going to return true. And this is a binary representation of decimal number 7. So we should get a value of 7 if we run this program. So if I run this, you see an output of 7 as expected. Let's change this to 2. Now as you can see, first bit is 0 and the second bit is 1. So this is going to return a 1. And in our last bit, both the bits are true. So in that case, this XOR operator is going to return a value of 0. Because XOR returns 0 if both the bits are true or if both the bits are false. So in this case, both the bits are true. So that's why we get a value of 0. And this is a binary representation of 1. So if I run this, we should get a value of 1. So as you can see, we get an output of 1. Moving on to our next operator, we are going to talk about operator known as left shift, bitwise left shift operator. Let's change this to 1. And now we know that we write in binary 2 as 1 0. Now this can be write in byte form, which is nothing but a combination of 8 bits. So to write it as a combination of 8 bits, we just need 6 more bits because we already have 2 bits. So we need 6 bits. So we are going to add 6 zeros before these 2 bits. And this whole is now a byte. And this byte represents a number 2. And what this left shift operator is going to do is that it's going to shift each bit in the first operand to the left by the total number of positions specified in the second operand. For example, in our case, each bit will be shifted to its left by 1 position. So this 1 will be shifted to this 0 position and the 0 will be shifted to this 1th position, and whatever remains will be filled with 0. So we will get this as output. As you can see, this 1 has been shifted from its current position to this position. Similarly, this 0 is shifted from its current position to this position, and whatever remains is filled with 0. So this is the output we will get. So if I run this program, this should give me an output of this, in which in decimal is number 4. So if I run this, we see 4 printed as output. Now what if I increase the number of positions to, let's say, 2? Now what I am doing here is that I am not shifting by positions by 1 but by 2. So instead of shifting this by 1 position, I need to shift it by 2 positions. So this will be shifted to not this but this. Similarly, this will be shifted to not this but this, and whatever remains will be filled with zeros. So this is the answer that I will get, which represents decimal number 8. So if I run this, you see an output of 8. Okay, now let's take the last example. Let's say I change this to 19, and let's say I shift it by 4, and a binary representation of 19 is. Recall that when we talked about data types in C, we said an integer stores numbers in 2 bytes or 4 bytes. So this is the first byte, right? So we need to add one more byte. The second byte will store zeros. So these are the 2 bytes. I have specified a space between them in order to separate the bytes. But remember that these numbers are not stored in memory with the space. So they are stored like this, without a space. Okay, so I have specified a space in order to separate the bytes and to make it readable. And we said that it can either store in 2 bytes or 4 bytes. So it can also represent this 19 like this in 4 bytes. We don't have to worry about 4 bytes, so let's talk about 2 bytes. So in our case, we need to shift these bits each by 4 positions to left. So starting from this 1, if I shift it 4 bytes, so this is 1 first position, this is second position, this is third position, and this is fourth position. So I need to place this 1 right on this 0. So I place it here. Then I need to move this 0 to 4 places. So 1, 2, 3, and 4. So it should be placed right here. Then this 0, 4 places. 1, 2, 3, and 4. Similarly, this 1, 1, 2, 3, and 4. This position. And similarly, the last one, this position. And whatever remains will be filled with 0. So this is the value that will be printed on the screen. If you have watched the video on binary numbers, then you can easily compute the decimal equivalent of this binary number. And the decimal equivalent of this binary number is 304. So if I run this program, this should print 304. As you can see, we get the output as expected. This left shift operator is used to multiply an integer with a power of 2. Just like this. Now let's talk about another bitwise operator, which is a right shift, which works similarly like left shift but in opposite direction. Let's change this to 1. Now instead of shifting the bits from right to left in case of left shift operator, in the right shift operator we do the opposite. We shift the bits from left to right. So this would be shifted right, but as you can see there is nothing on the right side, so this will be replaced with 0. And this 1 will be shifted to right, so we'll need to change this. After that, the 0 will be shifted to this 1th place, Similarly, this 0 will be shifted to 0th place, and this 1 will be shifted to 0th place. So we need to change it to 1, and that's it. So this is the binary representation that this right shift operator in our case is going to return. And this binary representation represents a number 9. So if I run this, we should get an output of 9. As you can see, we get an output of 9. Let's take one more example. Let's say I change to 260, and let's say this to 5. And 260 is presented as, okay, this is how 260 is represented. Now to make this easy, let's write all zeros. The first bit here is 0, and if I shift it 5 times, you see there is nothing after this 0. So you have to imagine that there are 5 zeros. So if I shift it 0 5 times, it's always going to give you output as 0. So it does not really matter for 0. Similarly for this 0. But for this one, if I shift it 5 times, this is the first, this is the second. And we have to imagine there are 3 more zeros in our case. So if I shift it 1, 2 and other 3 zeros, this 1 will disappear, right? Similarly for these zeros, we can shift it 5 places to right. And for this one, if I shift it 5 places, this is 1, 2, 3, 4 and 5. So we need to place it right here. And this is the last one, so we need to stop here. And at the last, this is the output of our program. So as you can see, this represents a decimal number 8. So if I run this program, I should get an output of 8. We get an output as 8. Just like a left shift operator is used in multiplying a number with a power of 2, similarly a right shift operator is used to divide a number by power of 2. Just like this. Okay, moving on to our last bitwise operator, which is known as binary NOT. This is also known as ones complement. And it's an urinary operator, so we only need one operand. So we are going to remove this second operand, and it's represented with this tilde sign. And let's change this to, let's say, 10. And let's write 10 in 2 bytes. This ones complement operator works like this. Wherever it encounters 0, that will be flipped to 1, and wherever it encounters 1, that will be flipped to 0. So it's simply going to invert the bits. So all the zeros will become 1, and all the ones will become 0. So this is the result we will get, and this represents a negative 11. And what makes it negative is because of this last bit. So in case of ones complement of a number, if this last bit is set to 1, it means this is a negative number, and if it is 0, it means this is a positive number. So in our case, this is a negative 11 number. So if we run this program, it should print a result of minus 11. So if I run this, you see an output of minus 11. Now let's quickly take one more example. Let's say I change this to minus 258. So the last bit will be set to 1 because this is a negative number. And this is how minus 258 will be represented. So each bit will change to its opposite value. So the 0 will become 1, this 1 will become 0, and so on. Now as you can notice, this last bit, which was 1, has been changed from 1 to 0. So which means this negative number has been changed to a positive number. So if I run this, we should see a positive value. So if I run this, you see a positive value, which is 257. Now let's talk about assignment operators. Now let's initialize this result variable to 2. So assignment operator is simply going to assign, is going to place a value in a variable. So this is one of the examples of an assignment operator. Recall that when we talked about arithmetical operators, we talked about increment operator, and that increments a value by 1. Now what if I want to increment a value by 4? So to do that, I can simply write it like this. So this is going to add 4 with 2, which is going to produce 6, and that 6 will be assigned to this result variable. So this 2 will be overwritten by this 6, and this can be written in a short form like this. This is going to add the value of this result variable with the operand 1, and then it's going to assign that to the result variable. So if I run this, it should produce a result of 6, as you can see. Similarly, we can change this to other arithmetical operators like subtraction. So if we run this, we see a result of -2. Similarly, we can change this to multiplication operator and run it, and we see 8. In the same way, we can change it to divide and run it, and we see 0. In the same way, we can change this to modulus operator, and this should give us a result of 2. And we can keep going on like this with other operators. But remember that logical and relational operators cannot be used in assignment operators because they work with expressions. But we can use the bitwise operator. So with this AND operator, this should produce a result of 0. Similarly, we can use OR operator or bitwise operator, and this produces a result of 6. And we can also use, so if I run this, you see an output of 6. Similarly, I can use left shift operator, bitwise left shift operator. So if I run this, we see an output of 32. Similarly, we can use the right shift operator, which gives an output of 0. And I think that's it. And as always, I'm going to give you an assignment that you can send on my email, which would be in the description of this video. So the assignment is given two operands 14 and 5, and using only 3 bitwise operators, which are XOR and left shift. You have to find a sequence or order in which these operators can be used to get an output of 133. And with that, I am going to end this video. If you like this video, give it a thumbs up and subscribe. I will see you in the next video. Till then, take care.